Good afternoon, everyone. Day 4, session 1. Today's first session is on hydrologic simulation models and virtual reality application for floods. I request Dr. Ramesh to deliver his lecture.
Thank you, Professor Yadav. I will start my lecture in a second. I'll share my screen first. Okay, so hopefully you should be able to see the screen very well, no problem.
Yes, sir. Yes, sir. We can see your screen.
Okay, so let's start today with the topic of hydrologic simulation models, and we all know that we do have different types of models which we can develop using computers. So within that simulation models, there are different types of approaches in the sense that some tools will provide you where you can build a model based on pre-specified objects. Like for example, in HEC-HMS, you have a reservoir, you have a stream reach, you have other types of inputs that you can easily drag onto a canvas, and then you can build your hydrologic simulation models. So those are, even though we don't call them as object-oriented simulation models, but we can still, in a way, we can call them as object-oriented simulation models, in the sense that we do have these objects, and these objects have some specific properties. Okay, so when I say specific properties, for example, a HEC-HMS has a reservoir object. It can only have some limited properties that it can inherit. For example, a reservoir, you need to provide some kind of a maximum storage, minimum storage, if there's any area versus stage relationships, or stage versus volume relationship, or stage versus discharge relationships. So those kind of objects have very specific properties. Of course, the person who is coding them can change the properties and give you a little more flexibility. So that's one type of modeling environment, which is we are quite familiar with, and this has been pretty beneficial because we have these different layers of models, different layers within the model, that in one layer you are basically dragging the objects onto a canvas, and in the second layer you are providing all the inputs required, and in the third layer you are creating what we call the control runs or simulation runs. Okay, that's one type of modeling environment. Then there are modeling environments which are more geared towards what we call water resources management specific applications. For example, there's a Riverware is there. Riverware is one of the softwares developed by Colorado State University Boulder, and they have a nice simulation model where you can again pull the objects and assign them, make them into a single reservoir system or a multiple reservoir system. You can simulate them. So that's again kind of following the same path of HEC-HMS, but mostly they are mainly for water resources management models. For example, there's a WEEP also, which is also very beneficial for water resources management option. And there are some other which are closely related to this kind of environments, where they recognize that in a particular field, you need a specific type of modeling environment and also objects, and they start providing that. So today I'm going to talk, in the first part of the talk, I'm also going to show you, I'm not sure if you're familiar with the concept of system dynamics, where we have only 4 objects which can define the entire process. Any process you can represent using those 4 objects. So system dynamics is a theory which evolved from MIT, Massachusetts Institute of Technology, and then it grown into a big area where a lot of applications come from business, environmental engineering, and then of course I worked with my advisor on this, and then we developed a number of system dynamic simulation models. So when you see today, I'm going to demonstrate a few things, and it will definitely impress you that some of the water resources problems you are building can be handled by system dynamics concepts. And then the advantage it provides is that because of the generic nature of the objects, you can come up with your own models, the interconnectivity between different components of the models. You can develop that. So that's the advantage of that particular system dynamics approach. So we do have two bifurcations. One is the dynamic simulation. When you say dynamic simulation is always with respect to either 2D or 3D, or 2 dimensions or 3 dimensions, plus a time component always included. Sometimes the space component is also included when you're talking about 3D or 2D, which is obvious, right? And then the time component, we call it as the 4th dimension, 3D, plus the 4th one is the time. So the dynamic comes from there, where the system is going through a number of changes with respect to time. And within that, you may have what we call positive and negative feedbacks. Positive feedbacks are those reinforcing feedbacks. That means, for example, if there's no control on the population will exponentially grow. But fortunately, we have some kind of control which happens. For example, the resource, what you call constraint, comes in. Or for example, if I give you an example of you dump several fishes into a small pond, they grow initially exponentially, but then after some time, the growth of the fishes inside a pond will go through what we call a sigmoidal curve in a form of an S curve, so that the growth evens out and then it becomes more of a logarithmic behavior. So it tapers off, and that's because of the resource and other limitations you have. So that means there are limits to growth, and there are nice books associated with that, famous books. The name of the book is Limits to Growth. Okay, so that's the positive feedback. But positive feedback cannot be sustained. For example, let's say water coming into a reservoir because of a flood, that is a positive feedback. You are continuously getting the water. The water level is exponentially raising because of the flood wave which is coming in. But the problem is that we will not allow it to go up in an exponential or any nonlinear fashion. What we do is we introduce what we call negative feedbacks. Negative feedbacks are those feedbacks which control the system in such a way that we get to a behavior what we are interested in. For example, you have the air conditioning systems, which are nothing but, or the thermostat inside your air conditioning system is going through what we call the negative feedback. It senses the temperature and then sends a signal, and then back happens the negative feedback. So we do have that. So the advantage with this type of simulation is that those are ideal for simulating water and environmental systems. Now, why it is advantageous? Because in case of water, if you remember, the main fundamental equation in water resources or in hydrology is the mass balance. The inputs minus outputs is equal to change in storage, and that works for any type of water resource system. Whether you take it as a soil matrix, whether you take it as a river, whether you take it as a lake, or whether you take it as an atmospheric water content or anywhere. So that's your fundamental E equals mc square equation, what we consider in hydrology or water resources. So that's your mass balance. Now, if you see, I'm offering 4 objects there. The 4 objects are stocks, which get filled over time. It's like a warehouse where you have a lot of volume, and then you can fill the stock. And flows, that things which are entering, things which are leaving. And converters, which help us to convert information into quantitative values. They take variable values from one end to another end. And connectors are basically which connect the information from one point to another point. Okay, so nowadays this is quite popular, the agent-based modeling, where you have trying to simulate the importance of highly variable quantities in space and time. Therefore, and then these variables have individualized behavior. For example, if you're trying to model the spread of COVID, that can be done by what we call agent-based modeling, where you have each agent, each individual is represented by an agent, and each agent has a behavior, and that behavior can be randomly simulated, and then we can see how many interactions are happening between two people, and ultimately we can find out the spread of the disease. So that's agent-based simulation what we are using right now. So in case of system dynamics, we are simulating the process within the confines of the boundary of the system, and we have some limitations on that, because once we define the system, we are not going to consider what is happening outside of the system. Sometimes you can introduce what we call exogenous shocks into the system. That means we can introduce variables which would affect the system. Okay, and we are doing simulation in space and time. So the simulation, virtual reality simulation, is slightly different, where we are trying to develop simulation with experiences of reality introduced into it, in the sense that whenever the users are encountering this simulation environment, they are embedded into an environment where they can expose themselves to reality, in the sense they feel like they are part of the realistic system. And nowadays there are lots of systems which are available which work on this concept, including you can attach them to your phones so that you can enjoy the virtual reality environment. And the other one is the immersive environments, in the sense, for example, if you want to understand, let's say, a molecular reaction, and that molecular reaction can be simulated, but sometimes we cannot see from outside, we don't appreciate it. But when we create an immersive environment, we can put yourself into the middle of that particular reaction, and you can start understanding how two molecules are reacting with each other, and then how the chemical reaction is happening and how they share the ions and so on. So in that case, the immersive environments help the user to get immersed into the system and appreciate the processes which are happening in that in any process. So that is how the immersive environment systems will work. So the second part is mainly looking at, for example, the floods. So why we would like to have a virtual reality environment for floods. So one important reason for having that kind of environment is that floods are dangerous, they're hazardous, catastrophic sometimes, and you cannot experience them by being part of the realistic system or outside. So therefore, you need to have some kind of a system which can simulate a flood situation, so that it helps you to understand the flood better, first of all. The second of all, if you're trying to educate students, especially civil engineering students who are working in water and environmental systems area or hydrology, in that case, they can experience the flood by being part of the immersive environment or without immersive environment, so that they can understand the concept of how the water level rises and where it spatially can spread, and what happens if I move from one location to another location. Can I see the extent of flooding? Can I see how many houses are flooded? To what level the houses are flooded? And can I introduce some kind of scenarios where I can introduce some structural measures to improve the flood protection? So that's the whole process of the second topic. So some of the materials what I'm going to use is from my recent book with Dr. Chandramouli. So this is about dynamic simulation and virtual reality in hydrology and water resources management. Of course, the dynamic simulation part is entirely written by me. Virtual reality, we both worked on a project where we developed this floodplain modeling, or at least immersive environment for modeling the process and understanding the process of how floods are generated. we used a realistic case study, real data sets, and then also we evaluated the effectiveness of the tool for students to see that if they are working in a 2D environment where they are just working with HEC-HMS and HEC-RAS, are they able to understand and appreciate the floods, or whether they work in the same environment and then they get attached to this particular immersive virtual reality environment, and then can they really appreciate the whole concept of flooding and so on. So that's the part of the exercise I'm going to discuss today. So the software is given to you, that is in the sense with a limited capability for you to expand on it because it's a case study specific, but still you can what you call unzip that particular zip file. It is 180 megabytes, so you should be able to unzip it and put it on your computer, and then you should be able to simulate the conditions, which I'm going to show you, and then appreciate. And one form of that version works also very well if you have 3D glasses with you, and that's also done in 3D immersive environment. Okay, so of course there's a lot of technical jargon, the type of modules they are using, and all those things. That is, I can provide you with the papers, and you can understand much better if you were to go into that field. But the idea is that you need to appreciate that there are tools like that which can help us in developing something practical. So what happens in research in United States is that most of the research is either driven by the industry. So industry provides money to research at schools or universities, and then the professors take up the research projects. So the first component or the major component of your thesis is mainly the research, the seminal or original research you're working on. And then the last part is the practical application, because that we do because of the requirement from the industry. The industry would also like to have a practical tool because they want to have something tangible. They are spending a lot of money. They would like to get something useful for their system. So simulation of the complex event. So what we do generally, we develop a model. And we should be able to have a simulation environment so that we can do what we call scenario analysis. And then typically what we do is we evaluate possible alternatives for catastrophic simulation events. So that, for example, a nuclear explosion or a terrorist attack or emergency evacuation during a cyclone system, or any other system where there is a blast at an industry, and then you need to model the whole situation and then try to see possible alternatives. How can you avoid that? So we do this emergency planning every year for our hurricane systems. When they come, we need to have evacuation routes planned. We need to have the traffic systems planned. We need to have operations for our canal systems, how much discharge we need to get into the ocean, and which part of the canal system is getting filled faster, which part of the system we are losing storage, and which part of the system which is gaining storage. So we have all these elements that needs to be simulated, and then we need to develop what we call possible alternatives before a hurricane hits the land in that particular area. So we can generate static and dynamic maps. When I say static maps, for example, you can take GIS and then develop what we call the inundation maps. Inundation maps will give you the spatial extent of the inundation, and then we will know exactly what might happen for a particular scenario. There can be dynamic maps, which is now more important because we would like to see dynamically as we start providing inputs what is happening to the system as we go. And sometimes static maps are more beneficial for emergency evacuation or operations. Politicians or decision makers will use that. Dynamic maps are more for modelers and people who are supporting these emergency operations. We can also be able to do what we call the real-time evaluation of the system, and then simulation along with animation. When I say simulation along with animation, that means we are not only just simulating the environment, we want to be in a situation where we can animate the whole thing. That means can we for example, it's like your flight simulator. You can simulate the system, but also you can animate. That means you can move around an area, you can move on top of something, or you want to change your path in one direction, you can do something like that. For example, in case of a flooding situation, I would like to go underneath the water and go into some area and see what is the depth of the water at that particular location, and how much of a house or how much of a building which is located in the central part of the town is flooded. So that also can be done with the help of animation. So for the virtual reality experiments, as I said, we are evolving into what we call immersive environments, which are already there. We can assess the improvement in student learning of any concept, for that matter, from chemistry to environmental engineering to civil engineering, and then we can evaluate complex processes. So let's go to first the dynamic simulation. These are some of the projects we have conducted. One is the development of performance indices for assessment of coastal structures. Watershed Master Planning Initiative. This is a research project where we try to evaluate the flooding in every part of Florida. We use what we call a simple bathtub model. That means based on the topography, we fill based on the soil moisture and soil capacity. We fill that with water, and we see how much water comes up based on the topography. And based on that, you define the flooding extent and the flooding levels in different parts of the region, and then that gives us a general idea about what is going on. Then 3D virtual reality modules for flood modeling studies, and then pilot study on catastrophic flood scenario animation for a region in South Florida. That's a very tiny project. Okay. So what exactly is dynamic simulation? Dynamic simulation refers to an explicit process of evaluation of system changes in space and time. Now, I'm also putting space there because most of the time the processes will have space. Models developed for evaluating changes in a system over time are referred to as dynamic models. Okay. Now we should not be confused between dynamic simulation and another word which will come later. It's called the system dynamics. So more or less the whole variations of these words are referring to models which can simulate over time. That's basically it. So when the spatial extent of the process to be modeled is identified and fixed, changes over time are critical for predicting the behavior in future. Okay, the stationary and non-stationary age of system depends on inputs of the system, and of course the behavior of the system. So sometimes in business and in industry, it is not the actual values of variables which are important, but the behavior of the system is more important for them. So typically a business environment is more interested in looking at trends, looking at the feedbacks which are affecting different things. So that is what is more important than just numbers. Okay. So what are the requirements? We need some kind of a visual depiction with complete different components. Scenario generation ability, visually to look at the feedbacks and interactions, quantitative expressions or equations to evaluate the system behaving in time and space. These are what we want. Separation of data and results and focus on the overall behavior than numerical values. That's again one of the requirements. User interface, of course, availability to check the model structure and validity, because when we are developing models, sometimes we don't know the process very well. So in that case, the structure of the model can be validated by checking whether this model is able to simulate the conditions very well or not. And also, we need to have some kind of uncertainty assessment for both input and output. That means that particular model should have sensitivity analysis features, and also probably advanced Monte Carlo simulation or Latin hypercube simulation based sampling based simulation. Ability to calibrate models through automatic and manual procedures, and then ability to conduct checks on dimensions, gain insights into interactions, visual depictions of changes, and ability to build reliable and robust simulation models at a rapid pace. That's what we want to do. User interface is very important so that we can analyze the scenarios. Ability to see the model components at different levels of detail. So, for example, in HMS and HEC class, you can actually click on the object and you can see the whole properties of that particular object. Separate qualitative and quantitative information, and share the models to other users, to other users actually, without having to have the proprietary software. So that's another one. Ability to import and export data from the simulation environment. So I already talked about the two categories of simulation environments. The first one is uses generic objects. The second one is more restrictive in the sense, for example, the objects are already decided. You have a reach, you have a stream, you have a diversion structure, you have something like that. So I'm looking for more generic structures. So the whole idea of system dynamics is originated from MIT. So the system dynamics is also a rigorous modeling method that enables us to build formal computer simulations of complex systems. Together, these tools can help us to create management flight simulators. When I say management flight simulators, when you're trying to manage a system, you would like to be in a flight simulation mode so that you can adjust the operations so that you can see what's going on into the future. Okay. Of course, this is all coming from a definition of a business world, but the reason why this attracted a lot into business world is that because in business world you have a lot of feedbacks, and these feedbacks are sometimes very difficult to model using Excel or any type of computer software. It's better to have a connectivity model where we can combine all these things so that you understand those. So what do we do in system dynamics? Simple. You identify the problem. We need to use systems thinking principles. What are systems thinking principles? Basically start with a big system, break it into smaller systems, understand the smaller systems, and try to develop the connections between these systems. Okay, identify all the variables in the system, identify the boundaries of the system, and then what we do is we can develop mental models. What are mental models? Develop conceptual models, which we develop on a paper. We write the connectivities and so on. Then we develop what we call causal connections, how the feedbacks between them are introduced. And then we take the whole thing and develop into a computer simulation model. We understand the behavior of the system, and then how we can replicate the structure of the model, and then we do all kinds of possible tests on it, and then we finally give the results to the stakeholders and modelers. So here is a simple example of how a system dynamics simulation model works based on the concept of system dynamics. Okay, so here you see the number of birds and the population. This is a positive feedback without any control. As the number of birds increase, population increases will create more birds and so on. So that's why I put a plus sign there, and then there's a positive feedback. This is the same thing, which is showing the same thing. You have the stock, you have the flow, you have the converter, that is converts the population and the birth rate. It multiplies into the birth rate. Let's say 20% of the birth rate is 20%. You can take that and then you add it to the flow, and the flow adds to the population. So this is without any negative feedback. That means this population will keep on going exponentially. But then if you want to introduce some kind of constraints, which are always there in our population growth models, you have resources which will constrain which will cause a number of deaths, and the number of deaths will deplete the population. So therefore, it reaches what we call a nice sigmoidal curve. So different dynamic behaviors are possible: exponential growth, exponential decay, then asymptotic growth where we have a desired level, asymptotic decay, oscillatory behavior, and sigmoidal shape behavior. There are other types of behaviors that are possible. So that means some of these behaviors are very common in our water resource in environmental systems. For example, we see a oscillatory behavior of your dissolved oxygen in streams. You see a negative feedback when a reservoir is controlled, because people are trying to control the amount of storage they can have, or they can control things so that we can get to a goal-seeking behavior. For example, there's a goal which you want to achieve, so you are controlling the system. So therefore, again, it's a goal-seeking behavior. So this is the complete model of your stock and flow diagram. So as you can see, 4 elements are required. You need a stock. Stock, as you can say in the English word, means that something which accumulates over time. You have the flow, and you do have sources and sinks. That means we get this data from somewhere and it goes into somewhere. So these are the two boundaries of the system, and we have connectors and converters. So you might say, well, yeah, population model is very good. Yeah, it really helps us to understand the system. But what about any other system? So for example, this is the one I developed some time back. This is a reservoir system where you can have inflows coming into the reservoir, you have discharge, and each of these discharges are modulated. We call it as a spaghetti meatball diagram. So basically what we have is all these connections which are helping me to understand the behavior of the reservoir as I introduce flows, and I can include evaporation losses, everything. The whole a reservoir system can be completely simulated. Similarly, a hydrologic system can be simulated. You can also simulate anything. So the beauty of system dynamic modeling is that you are not limited to the specific objects you get in HEC-HMS, okay, or HEC-RAS or WEEP. You have these four completely fundamental generic objects: stock, flows, converters, and connectors. You can take them and you can build them into a beautiful model where you can simulate the system. So for example, I want to show you a quick example of that. So this is a system dynamic simulation environment, okay, Stella, okay. It is called systems thinking educational evaluation and learning assessment or something like that, okay. That's an acronym for that. But you can see that there are four objects. For example, I can put a stock, and then I can put a flow. Okay. So are you guys following me what I'm doing?
Yes, sir.
Yeah.
Yes.
So what we can do is we can actually give an initial value of our reservoir, let's say 400, and then I can give the flow. How much water is coming in, let's say 30 CFS every. We can give it as a time function also. There are so many functions available. We can give it as a function of time also we can do, okay? So, but for the time being, I'm just giving a constant value. So what happens? This is a reservoir. I can change the name also if I want to, okay? Reservoir, and these are inflows. Okay, so what I built is a simple water resource system. There is a flow which is coming in. Now, as I said, this is versatile system. You can model anything. For example, the amount of anger you have is building up. So that anger is a stock, and the causative factors can be something which is slowly building up. So you can do that. You can model any situation as long as you can quantify them as stocks and flows. So this is the whole beauty of the system dynamics concept, okay? So now I have all these things. So I can actually look at the graph and double click on that. It'll tell me, okay, I want to see the variation of reservoir with respect to time, right? So when I run this model, what will happen? Anybody wants to guess? Oops, sorry. I have to go into there. I need to put it, okay. Okay, what happens when I run this model? There's a constant inflow which is coming into the reservoir, right? Agree? Anybody would like to comment on that? No, no one? Okay. I don't know if you're writing in chat, but I cannot see that.
No one has written.
Okay, okay. So basically, this 30, 30, 30 will get added to the initial value, so right? And so I go ahead and run it. So a linear behavior, basically every time 30 is added, of course, the initial value is 400, right? So this is how a system dynamic simulation works, where you have, you can build complex models using the four basic primitive elements: stocks, flows, connectors, and converters. So in this case, we are only using one stock, and we are using inflows. And then, of course, we can add more For example, if this reservoir is feeding into another reservoir, maybe I can add another reservoir like what we are doing in HMS or anything, and I can add it that one. So then I can define how much flow from this reservoir is going into the second reservoir and so on. Okay, so any observations or any questions you might have on this, the whole concept of system dynamics?
Sir, how the forecasting models are different from simulation models?
Okay, forecasting models are different from simulation models. There are 3 or 4 types of categories of models. One is, sorry, I will say 2. Okay, one is descriptive models. The other one is prescriptive models. Descriptive models are which describe the system. So all simulation models will come under the category of what we call descriptive models. They describe the system for us. They help us to understand the system better. They help us to play with the system in the sense if you change the inputs, you get different outputs. So that is your simulation. Whereas forecasting models are telling us what will happen in future. In a sense, they are also simulation models, but the main purpose is to predict what will happen in future, right? So at the end of the day, forecasting models are also simulation models because we need to understand the system first. We need to have a model of the system, but the primary aim is to what will happen in future, which every model is interested in. So that's basically simulation models. The prescriptive models are more of what we call optimization models. That means we are trying to optimize the system. So we are trying to prescribe something for the problems we have based on constraints and objective functions. We define our optimization model. So when we did optimization for our missing data, that is more of a prescriptive model. Okay, we are prescribing something, so that's a prescriptive model. Simulation models, which help us to understand the system, which will help us to understand the behavior of the system, both in space and time. That means when I say in time, that means over time, what will happen? That's basically a forecasting model. Okay, so I hope I clarified that.
Oh, yes, sir. Thank you, sir.
Any other questions?
Yes, sir. There is.
So, so in the illustration, the flow is unidirectional. Assuming that the flow is multidirectional, what will be the behavior in the reservoir accumulation?
Well, these flows can have a lot of properties. You can have whether the flow is going out of the reservoir. You can have negative flows. You can have positive flows. You can have flows which wait for some time before they go into the. So if you click on this one, there's a biflow is also there, and so on. So you can also introduce delays into your flows because this was mainly conceived for business applications, or at least initially when the simpler models were developed. They were also anticipating, for example, somebody can use it for an inventory model. In inventory warehouse models, you have some kind of delays. So, and we can introduce that also anytime in our flows. So obviously, the behavior of this system will be different based on the thing. So so that, I think that answers the question. Unfortunately, I cannot simulate a lot of scenarios, but the idea is that you have sensitivity analysis, you have Monte Carlo analysis within this one, and you can also look at the equations which are formed at the background. It's basically solving a finite difference equation for the whole model we have just represented, and that's your model. And then you can also build your own interfaces also, in the sense on the top, you can build, for example, let's say I want to change a factor for the amount of infiltration, right? I build a model for infiltration and I change a factor. Or for example, I want to see the flood hydrographs based on some variant of a factor. I can do that by introducing a interface there with a slider or some kind of users able to provide inputs. We can do that. And when you do the run, you see that sensi specifications. That means you are doing sensitivity analysis, and you're also doing by sectors. That means you can make the whole thing as one sector, and you can only run one sector. Okay, so there are huge applications where they have built models for whole country, for water-based models for the whole world. There's a world water model. You can search on that, and it is developed using system dynamics to understand the whole dynamics of the flow of water and how much we will have water in future. Okay. Any other questions? Of course, I can always delete these
Yes,
objects. Yeah, please go ahead.
How can we investigate the effect
Yeah.
of release from upper reservoir to the downstream reservoir or second reservoir?
Yeah, as soon as you put all your conditions here, in fact, I will show you a model which I developed. For example, let's see. Okay, this is one of the models which I was showing you in the screen. So if you see here, this is a complex model involving multiple reservoirs and multiple sectors. Okay, you can sometimes you can duplicate the same thing. But one advantage with that is that you can control the flows, you can control the spill, you can control how much water is going into the next one, how that water is. So this is a whole hydropower system model. So here I even developed a control panel, and you can see that this is my illustration of all the components in the model. And then, for example, here is my energy total power generation. So one thing is I can change a few things here. For example, I can say what is a flow which is reaching this particular one of the reservoirs names is Slave Falls. I don't know if you can see clearly or not, but of course small fonts. But I can run it, and the system can update the system. And then, for example, here you can see how the variations of power production at 4 reservoirs is changing. So, for example, let me take this, release this one, and I put it there, and then I can run the model. So you can see here how over the time how the simulations will change. So I have the sliders where I can control things. I can do a lot of things, and then this model is meant for simulation of a 4 reservoir system, hydraulically coupled. That means the tailwater of one reservoir influences the headwater of the other reservoir. They are short distance between them. They are runoff river plants, less amount of storage. So all those things. So in that case, you can see the complexity how this model can be easily developed. Then I'm also calculating what we call the indices. For example, I'm calculating reliability, how much there is a reliability in terms of power generation, vulnerability, how vulnerable is the system. Then I'm also talking about resiliency, so how fast power generation goes down and then comes back to the required generation ability, and so on. So we can introduce all kinds of indices, and this becomes the sectors of the model which a decision maker can easily understand. For example, if you're developing this model for a river authority in your area, let's say you want to simulate the Tapi River system with reservoirs in it, and then have a simulation model quickly ready. Now, somebody in that agency can quickly run the model by just changing the configurations of some of the values or see scenarios. They can generate thousands of scenarios. What will happen in a second once the model is completely built? Now, you can say, well, are you sure that the model is simulating correctly? Yes, because we go ahead and validate the model by observations. Unfortunately, there is no automatic calibration process, but if you have less number of parameters, you can automatically calibrate the process. Okay, does that help you understand how we can build complex models along with the interface? Okay, good.
Yes, sir.
Yeah, any other quick questions before we go on to the next topic?
No, sir. No, at present, no question in chat box.
Okay, so good. So basically, as I said, you might want to type system dynamics in Google. You will have thousands of references. But somebody who is starting their master's program or PhD program, if they are interested in developing generic models for water resources and environmental systems, their own models, okay? It can be a very complex process, but you are trying to understand the process and simulate the process and understand the behavior of the system over time. You can build your own models, and that will be very interesting. And these systems are very cheap. There are also free systems that are available. There are also systems which you can buy as a student, and then or with your research projects you can do. But the beauty which you have to appreciate is that the entire model is only made with 4 objects: stocks, flows, connectors, and converters. Everything can be embedded in there with the times, with graphics, something which is changing with respect to time. You can do sensitivity analysis, and it's a whole field by itself if you are applying for water resources applications. There are some good applications of water resource systems, but it would be interesting to develop these models for some problems where there is more knowledge that is being gained. So for example, you can simulate the groundwater system, you can simulate soil matrix system for irrigation systems, you can develop irrigation systems and evaluate their efficiencies, reservoir river systems, everything. Okay, let's go to the second part, which is the simulation with animation. Okay, this is the important part. We want to quickly go through this. So the idea is that we need some kind of simulation models to understand. For example, we have this static GIS maps which can tell us the amount of inundation and so on. But sometimes we need more than that. We need some kind of modeling or simulation environments to visualize the catastrophic flood events, okay, or some type of dangerous events which cannot be we cannot go into the field and evaluate those things. So there are 2 projects. One I'm going to quickly go through, and other one I can demonstrate. So the first one is the simulation and animation of a catastrophic flood event. The other one is simulation and virtual reality of a flood event. So this is a small pilot project we have done. So what we have done is we collected all the data, both topographic data and all kinds of structures data, canal data, and then the simulation results from a big regional simulation model which gives us the inundation depths of water at different places. Okay, that means the amount of water that will be occupied at any given time. Now that simulation model takes care into one of the most crazy scenarios, in the sense the deadliest hurricane, that is a cyclone, dumping tremendous amount of water, and there's a huge lake which has levees around it and that has broken. So this simulation basically tells us what is the worst case scenario where we will have the water. So we were using some tools including ArcGIS. Global Mapper is basically helping us to transform the data sets from one reference system to another one. There were 2 things we were using: Multigen Creator Pro and Multigen Vega Prime. This was a little 8 years back, but things have improved. So this is how the Creator Studio Pro works. You can take any type of data set, you can do your geoprocessing, and you can get your both DEM or any type of files. You can address them and you can change them. Then we use data sets from different water management agencies. That is SFWMD is South Florida Water Management District. We got the DEM, digital elevation models. We got the depth of the water level. We got the hydraulic structures information. We got the canals. We got the digital ortho quadrangles. These are basically geo-referenced aerial maps, like our Google aerial maps. And some of them we got from Google Earth just for validation. We bought some of them. We got from the agency also. So what we did was we created the terrain databases. We also converted the DEM to what we call the DED, the digital elevation data format, which is required for the software. And we created the 2D and 3D infrastructure drawings. And then we decided we can introduce what we call the video animation, so that we can have the 3D models, we can have simulation, and we can also simulate meteorological parameters, like our flight simulator. If you have ever played Microsoft Flight Simulator, it's exactly the same thing. Then we can create a flyby animation. So we fly over an area, we see the inundation, we can go within the water, and also we can look at that. So first, generation of the mesh required for us to evaluate a particular grid level in that digital elevation model. These are the structures, the hydraulic structures with the gates we created. We put them across the channels so that wherever they are existing. These are the roads we created so that when we are flying, we'll have some realistic feeling that we are moving on top of the roads. This is the Creator Pro, which can help us to create the textures for your objects. So we just created that. The textures and all those things can be created more closer to that. And then what we did was we created 2 levels of details. That means moving levels of details. That means if you go closer to the object, you get more details, but you fly away from the object, you get lesser details. So this really helps, because when you are trying to do a large-scale simulation, you don't need a lot of details to see. So it conserves the computational power, and it helps to display the raster images much faster. So for example, this is the coarser structure. Remember I was talking about the big lake. This is the largest, one of the freshwater largest lakes in Florida, in the country. And we did a simulation where this one breaks, the levees around this breaks, and then a hurricane comes in and then dumps a tremendous amount of water. And you see that only this side of the area is populated, the South Florida coastal areas. The middle part, they have some agricultural areas, and the bottom part is protected federal land, because it's Everglades, it's completely full of wetlands, and it is protected. So if you go for a finer level of detail, you go closer to the, then we have canal pathways. Then this is one of the flyby animations, like you can go on top of the area. And then sometimes we will see some issues. For example, this is the water, but there is also water showing in the sea. So that is another anomaly with the computer software which we are using. Again, it's the same thing. As you can see, you can fly on top of the cloud height, and you can see what is going on with respect to the flooding. So unfortunately, I don't have the exact flooding details, but I might be missing in this presentation for some reason. But what we have done is we have developed what we call a simulation with animation feature for us to understand the extent of flooding, and to see how the decision makers and operators and emergency management officials can go and run these scenarios, run these animations, and see where the water level will go up and which areas will be inundated. They can fly on top of those as if like somebody is flying after the disaster. So that really helps us. I told you there was a problem in some of the areas covered with water, even though it's not part of the land. That is what we call the Z buffer problem. That means the computer is not able to understand the differences in the topography, and that creates problems in inaccurate characterization of the flooding depth as well as topography. We saw that problem. And then the main recommendations was to reduce the spatial resolution of the data, to make it more on a scale which is like a small municipality or small township or a city or kind, so that it's much easier, less strainful on the computational resources. Okay, the next one is the virtual reality applications in flood simulation. So what exactly is virtual reality, which I think most of you are familiar. The young generation is very familiar with virtual reality. You have the virtual reality sets available where you can attach to your phones, and you can basically feel like you are on a particular journey on top of a mountain, or you are in Himalayas, or you are somewhere, and that experience is really realistic. So what we do is we combine a number of three-dimensional images which are generated. We create an immersive environment so that the users experience what we call the artificial version of reality. Okay, so of course we need a lot of things which to make the real-world experiences come realistic for you. So we have to mimic the real-world experiences, both physical and other aspects of the particular domain you're looking for, and also enable the users to fly around within the 3D environment and interact with complex data. For example, I can go and go inside a blast furnace and then stop a process happening. Or for example, I can say, okay, I will use a separator to separate a part of the chemical or a part of the material on one side. Or let's say I go into a cement, what you call mixer, and then I go inside and then I say, okay, I'm going to take off this much amount of adhesive or water from there, or I can remove this particular part of the concrete and see what happens to the strength of the concrete or how it mixes in a different way. Okay, so of course, VR applications are very beneficial. They use it in every type of training, space, pilot, and industry-related training, especially those areas where things are dangerous and inhospitable conditions. So these are some of the applications: archaeology, education, safety training, medical research, and these are discussed in the book, by the way, if you get hold of the book. So again, we use some simulation environments, and we want to get the results. We need to represent the system in a 3D environment, and that's what we have to do. So in that case, if we were to transfer virtual reality for hydrologic applications, we can do that. And I'm going to just give you a brief overview of what has been done. And we also use the end product for student assessment of learning, because in civil engineering, a lot of students might have not experienced a flood. They would have never seen a flood in their life, and they wanted to know how the flood looks like, how inundation happens in reality. Okay, so I will, for the lack of time, I'll quickly go through the whole thing. So we started with the data collection. We got through HEC HMS model. We got the discharges. Then we have a river stretch where we modeled using HEC-RAS. Then we took that data, developed into a virtual 3D model, and then we went through different universities so that we can experiment this tool and then evaluate by the educational expert. So this is a river system in Indiana, very close to Chicago. This is a Lake Michigan, and this is the main tributary. And there's a little Calumet River which causes flooding in this area all the time. So, and there are a number of reasons why this particular area was selected, because this area really helps the agencies to make decisions about where to construct the levees, where the flood will go, and how many houses will be inundated, and so on. So we did that, and we developed the HEC-HMS model by considering different basins. That's the main river, and we simulated the storm hydrograph. We evaluated it. Then we also developed the HEC-RAS model with 14 cross sections across the river, 5 across the Little Calumet River, 12 across the Little Calumet River East, and then 14 cross sections across. So all these things were done by students. They developed the models, and there was a catastrophic storm in 2008. Which dumped a tremendous amount of rainfall and created runoff issues, and then of course flooding issues. And then a HEC-RAS model was developed to model that situation. These are the flows and stages, and you can see that on that day in 2008, 9/1/2008, September 1st, that's when the flooding happened. And we use different types of data sets, the same thing. And the software used was Unity 3D game engine, so that we can develop the whole thing. The houses, the roads, the signs, everything was developed by students painstakingly, taking the aerial images and developing that into this one. So let me go through this. Okay, before we go there, I'll try to close this software and then go ahead and open the animation software. What we have is the flood simulation PUC package that is also available to you. Let me go to 3D, and then I start the system. Okay, so depending upon, this was done at Purdue University Calumet. It is a small satellite campus of the regular Purdue University. So let me read. Okay, so this is how it looks like, and let me wait for a second so to load. Okay, so I have a control menu which I can see. So for example, different road cross sections, their elevations. Then I can see the water quality also. This was not modeled here, but water quality in the sense the sediment loads and so on. And we show the status, and then we'll have so I can go to any part of the area to see what is going on. So for example, I can go there, I can go there. And right now there is no flooding. The water is going through the system without any problem. So for example, this is a confluence point, and you can see how realistic it is for people who are interested in decision making, and they can understand what is going on at different confluences. So let's see if I can, so let's see, for example, I want to see the, what is that called? I can see the 100-year floodplain, I can see all those things, but I want to show the, what is that? That is my, this particular screen is deforming some of the tools. So I can't see them because I'm using a laptop. More functions, let's see, the tour. So when you hit a tour, it basically gives you the entire tour of the area. That is a township, and then there's a river which is running around the township, which causes flooding. And then you can see that. And of course, let's go to flow plot, and you can see that where we are right now. Okay, we are here, and let me go through one of the confluence points like here, and then move my flow here. Okay, so you can see that how the water goes up at the highest hydrograph level, just before the hydrograph goes up, and then you can start seeing the flooding happening in that area. So you can just move a little bit to see when it reaches the peak, and you can see the amount. Of course, this is a look at the extent of flooding here in this particular area. So if I were to move this one a little bit this side, you will see that it's not much flooding, but as you go into the upper hydrograph, and then slowly it recedes after some time as the hydrograph recedes. But at the top of it, this is the amount of area that is flooded. So I'll go to the Columbia Avenue, where you can see the amount of flooding, Calumet Avenue, and so on. The confluence point, we already saw that. And then let's go to the Columbia Avenue, where here, if I were to jump on top of the area, so I have this much. So now the students can evaluate. For example, you'll see that it is a little bit shady in terms of this double images are appearing. That's because this is in 3D. So you actually need a 3D glass to appreciate this particular simulation. So if you were to put it on your computers, please try to put it on the 3D environment, okay, or 3D glasses. So let's say if we put it in levees and see how the levees are protecting the whole township from flooding. Okay, this is with levees in, without levees in. So this is what students can really appreciate in terms of their learning assessment with respect to the whole flooding scenario. Now, this also gives a lot of advantage for the decision makers to actually see the extent of flooding, and they can actually go to different places and start looking for what is happening in that area. And sometimes this fuzziness is happening because of the two things. One is the resolution at which we are doing the simulation, also the use of that 3D glasses that might help. So let's say if the levees are in, but of course we didn't put levees here, we only put at some places where it is highly populated. So let's see if the levees are here. No, there are no levees. There's already a levee on this side. See, now we are stopping. Even if the levee height can also be adjusted, there's a sluice gate also. For example, we can keep it open or and so on. This is the floodplain. This is a 100-year floodplain again. If you want to see that, there's a shape and outline also. Remove that, and then so wherever we are experiencing the flooding, so you can see here the water has gone into the subdivisions. That means where people have houses, and then we didn't put the levee here, but in some places there was funding for levee. So this was basically helping them. So for example, if I were to move a little bit this side, you can see the water is almost coming towards that particular subdivision. Luckily, it is at a higher location, but the roads are inundated. So I can put the levee and control the flow in that situation. So the whole engine is the HEC-RAS simulations for a particular flood hydrograph are run in the background, and it throws out the results in the form of a text file. That text file is processed to find out the flooding extent and the depths and all those things, and then that can be immediately transported into this virtual reality environment. So all it needs is that specific text file, what we are using, and we are simulating for one of those catastrophic floods which caused a lot of damage in this township, and then you can see that peak discharges, how they can be controlled. Of course, there are lots of elements which you can play if you have the software with you, or at least for this particular case study, so you can always appreciate what is going on and how we can look into this one. This one doesn't have the levee system on, and you see that a number of houses are flooded, and you can appreciate how much water is coming to it because of that. Let's say if you go ahead here, you can see the extent of flooding, where if I were to move the hydrograph simulation, there's no problem there, and slowly, suddenly, the water level is going up and then starts filling up, and then it recedes as the hydrograph recedes. Okay, so any questions for me? I know it was very quick, but
Yes, sir. There is one question. What is the system configuration required for the VR simulation?
You can do it on any PC environment, so it's not a problem. Most of this done are on a higher end PC machine with a good RAM. That's it. And then the Unity 3D platform is available. I don't know the cost of it, but if you are having a research projects, you can definitely develop that. And these are some of the research questions we asked to the students before and after they were exposed to 3D environment. So we have a cohort of students in the first part of this semester where we explained about flooding and hydrographs and HEC-RAS and HEC-HMS and everything. And then in the second part, we said, you know something about flooding, you have simulated flooding in that particular area. Now let us expose you to the 3D environment, and then see how your understanding has improved in terms of structural flood control, or changing the sluice gate heights, or opening them, or changing the levee height, or changing the hydrographs, or how the hydrograph, as the hydrograph moves, how the water levels are changing, how the inundation extent is increasing. So it's like your dynamic GIS more or less, but still you have the benefit of having the 3D environment. You also have the immersive environment where you can go in and you can play. I mean, as soon as you have this joystick and the 3D glasses, you can do wonders with this one. So what we have done is we put this environment to 4 universities so that we have the diversity of students, and then we compared how they have learned before and after. We did all the statistical tests, and in the end it showed that students appreciated. And we did a pre-test and a post-test using technical questions, and that also showed that students have improved substantially in terms of their assessment of learning. And I think there are the end. So students who used 3D model rated their experience with the module highly. Vast majority described lab module as interesting and enjoyed interacting with it. Majority felt 3D lab enhanced their learning and helped them to link new knowledge with the previous knowledge. And this was some of the, and higher levels of engagement was there, and people could appreciate for the first time what a flood looks like. Many of them would have not seen a flood in their life. So that was the idea. Okay, so I guess if we have any questions, we can always deal it tomorrow. Yes, please go ahead and ask a question. Dhruv Patel.
Yeah, good afternoon, sir.
Yeah.
I would like to know, sir, that how we fix the station points for levies. How far it is from the banks, or either we can propose exactly on the banks, or how we means find out that.
This is based on the specific region, what the students have gotten the information from the site. But the levee height and all those things are mostly for scenario analysis. These were not done with any local municipal guidance or anything. We had a flood in 2008. That was the catastrophic flood. So what we have done is, take to the current existing bank full discharge conditions. You move a little bit away into the flood zone where the government was thinking about constructing a levee or a berm, and we decided to put a artificial barrier in our simulation. Basically, we said that water cannot go beyond that and whatever storage. So that's how we could limit the flows. That's it.
And sir, what resolution of DM is required? That means any optimum resolutions definitely we require to propose the levies in the river.
Well, one thing is that for this particular, you're talking about the resolution of the DEM, right?
Yeah.
Yeah. So again, for the computing environments to be reasonably faster, you need to have not more than 10-meter resolution DEMs. We also have 1-meter resolution also, but then it needs a higher end computer to have that smooth moving effect. Otherwise, you will have sketchy effect because it has to load all that information. So that is the problem. Yeah. So we have to do a trade-off. We have 1-meter DEM resolution. We have 10 meters. We have 30 meters. We have 100 meters. So for initial applications, 100 meters is fine just for the sake of understanding. But to get the field level variations, I think 30 meters will do for a flooding situation.
So what's usually which are accepted in USA for flood vulnerability hazard mapping?
The flood mapping, we typically go because flood mapping is done by like a state, like in India, like county we call it in US. So they go with the best resolution that is available, which has the best vertical accuracy. So currently, if they have a LiDAR data, which has 1 meter, less than 1 meter, but if the accuracy is bad, they will not go for LiDAR data. They will go for a DEM, which is standard, which is produced by a federal government, and it has enough vertical accuracy so that it will not throw off this, the results, and it can be defended in a court of law. So we have to make sure that when the county does the job, they have to be careful, because citizens can sue the county saying that you used the wrong DEM and then you told that our house will be in flood zone, but in fact it is not in the flood zone. So we have to be careful. I served as a reviewer for flood mapping studies, and in that case, we have to be very careful because we anticipate lawsuits from citizens living in that area. That's what.
So one last question I would like to ask, time permits. Sir, do you have any experience for whether any soil degradations in the river which has the effect on flood inundations?
I have not done any work, but I think there is
effect either we have or not.
I mean, in this context you are talking about, in the simulation context or in general?
In the flood inundation context, suppose we will include aggradation, or maybe we not.
No, they will not. They will not go to that detail level. Basically, they do a multiple soil moisture scenarios and multiple precipitation scenarios, and they generate this 500-year flood zones and 100-year flood zones and all those zones, and they create maps, and they call it as DFIRMs, digital flood insurance rate maps. They create them and they post it on public domain so that even I can see where my house is located, whether I'm in a 500-year flood zone or a 100-year flood zone. And then I can argue with the insurance agencies about my insurance. I can do that.
Yeah. Thank you so much, Professor.
No problem. Thank you. You're welcome.
Sir.
So I guess we will stop here,
Yes, sir.
right,
Yes.
Professor Yadav?
Yes, sir.
And then
Dr. Dhruvesh Patel is associate professor at Pandit Deendayal University, Gandhinagar.
Oh, thank you.
Yes.
Yeah, I saw that. He was talking before.
Yes.
Yes.
Nice to meet you, Dr. Patel. Nice to meet you.
Thank you, sir.
Yeah.
Thank you so much. I'm so
Sir,
curious
we will
to know
have-
actually how it works. That's yeah.
We will be in touch. I mean, my email is available everywhere, so no problem.
Ji.
You can communicate with me anytime. Yes.
Ji, sir. Thank you so much, sir.
You're welcome. Yeah. I will
Dr.
stop
P,
presenting. And
We'll have a quick break of 5 minutes, and exactly at 5 o'clock we will rejoin.
5. What is the time now? Okay, so I will be a little late, sir. You start the process.
No,
Okay.
actually, sir,
Is that
sir,
possible? Is that okay?
it's a panel discussion, so your presence is required. So what time you will be?
I need to. There are 2 things I need to do because I am leaving on Saturday. I need to go to administrative office and do some signatures for my stay reimbursement or whatever here. So that is one thing. And the other one is that I need to grab something before we start so I might need 20 minutes if possible.
Actually, we have invited guests also. So I think 5:10 will be fine. 5:10, 15 minutes will be fine.
Okay, you start the process. I will join as soon as possible. Okay.
Okay, sir. Okay.
You start don't delay the process. We'll start the process, and then you have my questions also. And let us because we have 1 hour discussion anyway.
Okay, sir. Okay, sir.
I will join.
Take photograph.
Yes, sir.
Please turn on cameras, everyone.
Okay.
So everyone, please be quick. Participants, Rashmi, be fast. Done, Rashmi?
Yes, sir. I have written.
Okay, sir.
Thank
Okay,
you,
sir.
everyone.
Thank you.
you.
So we'll meet at 5:10. Okay.
Okay. I'm done.